In this presentation, I will talk about chemical equilibrium. Um, we will try to define what it is and also define some important terms and values that we use when dealing with chemical equilibrium. So we'll look at what is this chemical equilibrium. An important expression that we use in chemical equilibrium, that is Kc. So Kc is a very important expression when discussing chemical equilibrium. The C, the small c that you can see there, is means concentration. Kc, equilibrium constant depending on concentration. We should also be able to calculate Kc using equilibrium concentrations. So if we know these are the concentrations of the species of the products and reactants at equilibrium, we can calculate the Kc for that reaction. And also we should be able to calculate equilibrium concentrations if we are whenever we are given initial concentrations. What does initial concentration mean? It means the concentration of the species that we have before equilibrium. We can start with a higher concentration, and the concentration of the reactants will be decreasing until it reaches equilibrium. So at that point before equilibrium, the concentrations that we start with are known as initial concentration. Then we will also look at the relationship between Kc and another equilibrium constant that we call Kp. P stands for pressure. Instead of using concentrations, in this case we use the pressure of the reactants and products. We will also determine factors that affect equilibrium, and then Le Chatelier's principle. That's one important principle. We cannot study equilibrium without talking about this very important principle. Now, let us consider the following reaction. So, for this reaction, we can see that the reaction is going this way. So we take this reaction as what we call a forward reaction. But then there is also another reaction that can happen, and this reaction is going a different direction, that is this direction. So this one, this reaction number 2, is the reverse of reaction number 1. So in this reaction we have both the forward reaction taking place, and after some time we also have the reverse reaction taking place. So what happens? What happens is that at equilibrium, the two opposing reactions will occur at the same rate, and then because of that, the concentration will not change. The concentration of all the species involved will remain constant at that point. That does not mean that the concentrations will be equal, no, but the concentrations will remain constant. They will remain the same. They will not change. For example, if calcium carbonate at equilibrium has the concentration of 0.5, no matter how much time passes, the concentration will still remain 0.5. If carbon dioxide has the concentration of 1 molar, no matter what happens, but when the equilibrium is reached, the concentration of carbon dioxide will remain 1 molar. That's what it means. The concentration of species do not change once equilibrium is established. Now, how do we express the equilibrium constant, especially if we are given an expression or a chemical reaction? So let us consider this expression. And you can see we have WA plus XB to give us YC plus ZD. The difference between letters that we have, we see that W, X, Y, and Z are given in small letters. The letters A, B, C, and D are given as block letters. What does that mean? The small letters are just coefficients of the reactants or products, while the big letters are the actual species that we are reacting. For example, if A is H, then you can say W is 2 hydrogen, so 2A. So how do we express the equilibrium constant given an expression like that? So the equilibrium constant is expressed by the concentrations given, starting with the concentration of the reactants, that is up at the top, not at the top, I mean starting with the concentration of the products at the top versus the concentration of the reactants at the bottom. So these ones are the products, while these ones are the reactants. So you need to start with the products at the top and reactants at the bottom. And your coefficients should be the powers of each concentration you are dealing with. For example, D here or C here has a coefficient of Y. So this is your C here, and your Y coefficient is given as the exponent of C. D here has a coefficient of Z. So this is your D here, and this is your Z coefficient. So you do the same thing for the reactants, but always the product should be on top and the reactants should be at the bottom for the forward reaction. So this is just the introduction to this chemical equilibrium. The numerical value of Kc, therefore, is calculated using the concentrations of reactants and products that exist at equilibrium. So if you want to calculate Kc, you need to determine the concentration at equilibrium. Before that, it's a different case. It's no longer Kc. So these are some of the examples how we express the concentrations. So you can check this one. Thank you.